Let us bow our heads. Dear Heavenly Father, Lord, thank you so much for today as we study about the organized unit of the atom and see the intentionality that you put in place. That is the foundation and the building blocks of everything that is created in this world that we can touch, that takes up space, Lord. I ask that you please help us to reflect on you and be able to look at whatever message you have for us today, beyond the information in this class, but also just the intentionality that you have, and that how that intentionality reflects on us as individuals. In Jesus' name I do pray, amen. All right, so let's get started. Making sure that this is not in your way. How could I hide that? All right, I think that works. All right, so last class we ended up talking about the fundamental and powerful concept. And as we're going through this lesson, I just want you guys to look for the details that will help you understand this information at a deep level for critical thinking. And again, today we're just going to start off with the basics, general chemistry review. So it shouldn't take long. We're going to just get through this. We're going through chapter 1.1 through 1.5, and then we're going to end it with chapter 1.12. All right, so let's go. So we know, well, I hope we all know that the smallest organized unit is the atom. And within the atom, you have your nucleus, okay? We have your nucleus, which comprises of your protons and your neutrons. And if you guys remember, protons are positively charged and neutrons are electrically neutral. Okay, so they do not possess a charge. They simply just add weight to the overall atom. Now, surrounding this positively charged nucleus consists of subatomic particles, in addition to that, which are your electrons. And your electrons are orbiting your nucleus, creating a cloud. Okay, creating a cloud. So let's break apart some quantifying measurements within this atom. So the first thing is your atomic number, okay, your atomic number. Now this is the number of protons in an atom's nucleus. So your atomic number is the element or the atom's ID number, if you will. So based on the atomic number, which is the number of protons, that gives the identification to that atom. So all hydrogen atoms are going to have one proton. If you add an additional proton, you have two. That's now helium. So the ID has changed. So I say the atomic number is the atom's ID number. Now, next you have the mass number. Do not get the mistake. The atomic number is simply only taking into account the protons, while the mass number is looking at the protons plus the neutrons. And so that's the overall mass, because remember, the nucleus is what gives the atom its mass, okay? The majority of its mass comes from the nucleus. And within that nucleus, you have protons that are positively charged, which is what gives that atom its DNA, its ID, and or its identification, its properties is what that is, that protons, right? And then the neutrons is just giving extra mass, and so that's your mass numbers. The atoms of a given element will always have the same atomic number. So I kind of said that before. The atoms of a given element will always have the same atomic number. You're always going to have the same amount of protons. So helium will always have the same amount of protons all the time. hydrogen, oxygen, carbon. Those are all going to have the same atomic number as itself, okay? So carbons will always be carbons and so forth. Now, isotopes will have the same atomic number, but the mass number will be different. And that's because with isotopes, while the proton stays the same, the number of neutron changes. So if I have carbon, let's say carbon 12, okay, if I have carbon 12, that means I'm going to have 6 protons, okay, and I will have 6 neutrons. That equals a total of 12, okay? So if I have carbon 12, that's going to be 6 protons and 6 neutrons. But let's say if I have carbon 13, the protons is always going to be the same, but the number of neutrons is going to be different. 6 plus 7 is 13. 6 plus 6 is carbon. So those are going to be isotopes. Those two are isotopes. A very common isotope that you guys are going to hear in this class is the isotope dealing with hydrogen. Okay, so hydrogen has actually 1 proton, and there are no neutrons in hydrogen that we know, okay? However, in organic chemistry, you're going to see a D sometimes instead of an H, and that is deuterium, okay? And deuterium has 1 proton, and it actually has 1 neutron, and so that is deuterium. So this is going to have a mass number of 2. All right, so you have hydrogen and deuterium. And I just bring that up because later on, you're going to see where that's D. You're going to see that D in different areas that looks like, wait, why is there a D there? It should be a H. Well, that D is actually deuterium, which is an isotope of hydrogen. Now, atomic mass or the atomic weight is actually the weighted average mass in atomic mass units, AMU, of an element's naturally occurring isotope. So when you're looking at the atomic mass, okay, or molecular weight, the atomic weight, these are all synonyms of each other. What you're actually looking at is, and when we talk about and do an example, I'll bring it up again. What you're talking about is that if I took a scoop, let's say if I took a scoop of dirt, within that scoop of dirt, I'm going to have different types of carbons, isotopes. I'm going to have different oxygen isotopes. I'm going to have different nitrogen isotopes or so forth, okay? That atomic weight is if I took the average mass weight, okay, atomic mass unit, AMU, of based on the composition and percentage of each of those isotopes in the nature. And again, as I'll explain it a little bit better in a little bit, okay? Definitely explain it better later. All right, when I can visually show you guys. All right, so next we're going to talk about orbitals, okay? The atomic structure and dealing with orbitals. So now we're talking about the electrons. Now, a wave equation is a mathematical equation which describes the behavior of a specific electron in an atom. So we're looking at the behavior of a specific electron. And that wave function or orbital is a solution of the wave equation, okay? So the wave function or orbital is the solution of the wave equation. So you have a wave equation, and its solution is the wave function. Now, an electron cloud has no specific boundary. All right, electrons can go and move as it will. There's no actually specific boundary. However, when we're looking at the electron cloud or we're looking at the shape or the path of the electrons, we're looking at the most probable area that the electron is going to occupy, okay? So we're considering the most probable area of that electron. So I'm sure you guys remember from general chemistry, you had different types of orbitals, okay? And this again is the area most likely for the electron to occupy. So you have an s orbital, you have a p, d, and f. These are the different kinds of orbitals. Now, in organic chemistry and biological chemistry, so your biochemistry, and looking at the chemistry of biological organisms, we're usually dealing with the S and P orbital, and we're looking at the interactions of those orbitals. So the S and P orbitals, those are the most common ones. Now, as you guys can see here in this diagram, the S orbital is going to be a spherical where the nucleus is at the center, okay? So if you look here, this is the nucleus, and the electrons are going to occupy, creating a spherical shape, if you will, okay? So it's a sphere. Now with the p orbitals, you get this dumbbell shape where the nucleus is in the middle. So you have this dumbbell shape of where these electrons are occupying and they're moving, okay? Next, we're going to talk about the d orbital, and we're just going to go up to the d orbital when we're dealing with organic chemistry. With the d, you have elongated, so it's an elongated dumbbell shape, okay, where you have this, and this is your d, this is your d orbital, okay? So when you see an orbital like this, it's S, P, and D. And again, this is just the area that the electrons occupy, most probable occupying. All right, so orbitals in an atom are organized into different electron shells, all right, centered around the nucleus in shells of increasing size and energy. So as your have different shells, all right, the orbitals that have different shells, they're going to be increasing in size as well as in energy, okay? So increasing in energy. Now, different shells contain different numbers and kinds of orbitals. Each orbital can be occupied by 2 electrons, okay? So each orbital occupies 2 electrons. Give me 1 second. Okay, here you can see, all right, here you can see that the energy levels of electrons in an atom. So in the first shell, you have 1s. And I can show you how this coordinates with the periodic table. What I think I may do is do a follow-up video talking about identifying the shells and on the periodic table, okay? So this right here is 1s. As you can see in this orbital, you have 2 electrons, one north, one going south. Next, as the energy increases, you have 2s orbital, and the 2s orbital has 1 orbital in there, one going up, one going down. Now the 2p comprises of 3 orbitals, x, y, and z. And so in the 2p, you're able to hold a total of 6 electrons, okay? And then next you have your 3s, which has 2. So if you notice, your s orbitals only have 1 orbital in, or your 3s shell has 1 orbital in it, and then your 3p shell and this third shell here is 3p. You have 3 total of 6, okay? And so this pattern you're able to see there. And then in your 3D, you have 5, which means it's a total of 10. So the first shell can only hold 2 electrons. The second shell, because it consists of 2s and 2p, can hold a total of 8. And then your third shell can hold a total of 18 because you have 10 plus 6 plus 2. So if you're ever trying to figure out how many electrons something can hold, you don't actually have to memorize it. You can actually just use your periodic table and kind of understand where those electrons are coming from. All right, so here's the opportunity for us to look at this question. I don't know why it's not showing me. Let's see. Or I'll read the question out loud. It's asking, how many electrons does magnesium have in its outermost electron shell? So the question is how many electrons does magnesium have in its outermost electron shell? So if we look at magnesium, and this is the chance we can look at this periodic table here. Matter of fact, let me get out of this so you guys can actually see it better. I don't like how this is showing. So I'm going to duplicate it a couple of times. If you guys just bear with me. All right. So let's see what this does like this. Okay. So again, how many electrons does magnesium have in its outermost shell? So let's look at this. So if we're looking at the periodic table, okay, what you can see is magnesium, which is number 12, element number 12 is here. Now, if you look above all of these here, you are able to see where it possesses. Now, again, in organic chemistry, we're focusing mainly on the s orbitals, which is what s, 2s, or 1s orbital, 2s. So you're looking, this right here is your s block. So both of these, you're looking at your s block, okay? And then if we come over here, this right here is your p block. S, and this is P. Okay. So when you're looking at these, what you can tell is based on the outer shell, the element that is in different groups, okay? The elements are organized into different groups. And so in this group, they all have one electron in the outer shell. This group has two elements in the outer shell. Now, these groups over here, which are your transitional metals, they follow a different pattern, so we're not going to discuss those, okay? But over here, you have, so you see the 3A here? These here have 3 electrons. These have 4 electrons, 5, 6, 7. And then by the time you get here, it becomes a full shell, okay? So if I'm asking how many electrons are in the outermost shell of magnesium, you're going to take in consideration that elements of the periodic table are organized into groups based on the number of outer shell electrons each element has. Okay, so all of these are in the group, and which why they have the similar properties is because they all have the same amount of electrons in the outermost shell, which is 1. And then the next one has 2. Then we have going forth 3, 4, 5, 6, 7, and this is 8, which is completely full. Okay, your outer shells, those are your noble gases. So when we use the periodic table, locate the group of the element magnesium, which we just did, and magnesium is in group 2A, which means it has 2 electrons in the outermost shell. Now, these electrons in the outermost shell, we refer to those as valence electrons. An outermost shell is of valence electrons. These are important electrons because these are the electrons that are interacting, which create the chemical properties of that element. So these are the electrons that the atom is donating or receiving. It's in that outer shell. Now, within those shells, when the what drives them, the interactions and the chemical reactions, is because the atoms are trying to become stable like noble gases. And so it's either going to give up an electron or accept an electron to become closer to the noble gas. Now, when electrons are actually moving from one atom to another and aren't really being shared, but are actually being stolen and taken away. Those are called ionic bonds. So these are ions that are held together by an electrostatic attraction, which is formed as a result of the electrons being transferred. So if I'm looking at sodium chloride, now if we think about it, sodium is in the first group, so that has 1 electron, where chlorine is in the 7th group, so it has 7 electrons. So sodium has that 1 electron here, and then chlorine has the 7 here. Okay, so for sodium to become noble, it needs to lose 1 electron. For chlorine to become noble, it needs to gain 1 electron. So what's going to happen is this electron here is going to be stolen by chlorine. And that is going to result in sodium having a plus charge because it lost that electron, which was stabilizing and making that atom stable. So atoms are neutral. The protons and the electrons equal the same. So the same amount of protons that sodium had was the same amount of electrons it had, so it was completely stable. Once it lost that electron, it now had 1 extra proton more than electron, hence it giving it +1. Whereas now chlorine gained an electron, has 1 extra, because chlorine has 1 extra electron, the overall charge of chlorine is now -1. So you have +1 and -1. And so they're attracted to each other because of this electrostatic, okay, attraction, and that is going to cause them to kind of stay with each other. However, they are able to, in aqueous solutions, be pulled away from each other and dissociate. Conversely, covalent bonds are not actually when elements or atoms are losing or gaining electrons, they're actually sharing electrons. And so covalent bonds are formed when 2 elements or 2 atoms share electrons to become more stable. And we're going to see that in organic chemistry. So now that we understand what valence electrons are and the ionic and covalent bonds, we're going to talk about carbon specifically. All right, so Kekula and Cooper independently observed that carbon is tetravalent. And so from their discovery and their observations, Jacobus, Van 't Hoff, and Lebel proposed that the 4 bonds of carbon have specific spatial directions. And so they were able to, let me get my highlighter, pointer. So they were able to show that the atoms surrounding the carbon are surrounded at the corners of a regular tetrahedron. So this is a tetrahedron. The atoms are going to be separated as such. And here you can see where this wedge is and this dash is. These are elements coming out and in. So if you're looking at it, you have 2 carbons in a plane, and then you have, or not 2 carbons in a plane, but you have 2 atoms in the plane from the carbon, and then the 2, one facing you, and then one facing back, okay? And so that's a tetrahedron. So if my middle of my hand is the carbon, we're looking at it this way, we have 1 here and 1 here that's in plane, and then these 2, one's forward and one's facing you. All right, so here goes an even better representation and visual of that. So here you have your singular carbon atom, and then the hydrogens here are in the same plane as each other. And then in this one hydrogen is facing forward and the other hydrogen is facing back. And you can see that 3D model here, okay? So two of the atoms that are attached to a carbon will be out of plane of the carbon. All right, so the natural collection of atoms that are held together by covalent bonds, that is a molecule. So whenever you hear the word means say referring to the molecule, we're looking at a natural collection of atoms that are held together by covalent bonds. Now, electron dot structures are representation of these valence shell electrons of an atom as dots. And so these are Lewis structures. I know you guys have remembered hearing those from general chemistry. So we're going to have the Lewis structures, and these are synonymous with the electron dot structures. And then last, we have line bond structures, and this indicates two electron covalently bond by a line. So whenever you see that line, you're able to know that that line represents two electrons that are covalent bonds with each other, okay? And those are called Kokilla structures. So let's go in and look at that. All right, so here you have your electron dot structures, your Lewis structures. So if you notice, this hydrogen is bonded covalently to this carbon, okay? And you see these two dots. Those two dots represent that sharing of electrons. And you see that around the whole thing, okay? Here's another example of a Lewis structure here. All right. And again, with this nitrogen, because nitrogen has 5 valence electrons, 3 of them are being able to be shared with the hydrogen in this case, and then the other 2 are alone. Notice the colors of these, okay? Next, you have water, okay? And so with your water one, again, you're seeing the sharing of electrons, and you have 2 sets of lone pairs because oxygen has 6 valence electrons. And then this right here is a little bit more complicated. This is actually methanol. All right, this is methanol. And with methanol, you have what we call a hydroxyl group on it. All right, an OH group. This is methanol. So these are the Kokilla structures of these same molecules. And so everywhere where you have those 2 electrons being shared by an atom, you're going to draw them as a bond. However, in Kokilla structures, when you show the lone pairs, as you see in the last 3, they're going to be shown still as individual electrons because they're lone pairs, okay? So just when the bonds are being shared, you draw them as lines. Right, so the number of covalent bonds an atom forms depends on the number of additional valence electrons it needs to reach a stable octet, okay? So carbon has 4 valence electrons, 2s2 and 2p2, which allows it to form a total of 4 bonds, okay? Because if you have 4 valence electrons, to get to 8, you need 4 more. Now, nitrogen has 5 valence electrons, okay? It's 2s2 and then 2p3, forming, so that way it can form 3 bonds. So how do you see that? So you need 5, well, you have 5 valence electrons. To get to 8, you need 3 more. Therefore, it can form 3, okay, let's see, 1, 2, 3 bonds, but it leaves you with the 2 lone pairs, okay? So let's zoom in so you guys can really see this. And let's actually start with hydrogen. Okay, so hydrogen has that 1s1 orbital with just that 1 electron in it, okay? Now with the 1s orbital, we know that it can only hold 2 electrons. And so to get the octet or to get the full orbital, it doesn't need 8, it just needs 2. So if you have 1, you only need 1 more to get to that perfect 2. And since it needs one more, only one bond can ever be formed to hydrogen. You cannot have hydrogen bonded to more than one thing because that shell, that orbital can, or that shell can only hold one more electron, making a total of two, okay? When you have carbon, as we mentioned, carbon has 4 valence electrons. Now, with the 2s orbital and then the 2p orbital, you're able to get a total of 8, okay? So that second shell can have a total of 8. So with that 4, it needs 4 more to create that octet. And so again, as I said, it needs 4 more, and so each of those 4 more bond equally, give you those 4 bonds. So for nitrogen to be happy, you have 5 valence electrons. To get to 8, you need 3 more. So those 3 more create the 3 bonds that you see in nitrogen often, so that it's nice and happy. And then you have 2 more lone pairs that you see here, okay? You see these 2 lone pairs. That's because we can't bond with those to make it happy. All right. Oxygen has 6 valence electrons. So how many valence electrons does it need? All right. So it needs 2 more. When you have 2 more, so let's say we have 6 and I only have 5 fingers, so it's going to be a little hard to do this, but say we have 6. If I have 2 more, those 2 more are going to create bonds. And then if what do I have left over? I have 4. So after I bond the 2, I have 4 left over. And those are the 4 lone pairs, the 2 pairs of lone pairs, which equal a total of 4. All right, you have 4 lone electrons left. Now, last you have your halogens. Remember, in organic chemistry, the halogens are what we look at as well. They're very common in organic chemistry. So with the halogens, you have 7, valence electrons. Because you have 7 valence electrons, and again, we're getting this based on the organization of the periodic table. If you guys look, remember, if you need to go back, you have 7 valence electrons. So how many more do you need? You need 1 more electron. And so that 1 more electron is going to create that 1 bond, leaving you with 6 electrons left over, which is a set of 3 pairs of electrons that we see around each of these. 1, 2, 3, or I can say 2, 4, 6. Okay. Oh, just looking a little bit more at the non-bonding electrons. So lone pairs, which are valence electrons not used in bonding, okay? So the lone pairs are valence electrons not used in bonding. For example, nitrogen atom and ammonia, they share 6 valence electrons in the 3 covalent bonds, okay? So we see that. And those shared electrons, all right, if you see in the Lewis structure here, or you can look at it in the Kekula structure here. And the 2 of the other valence electrons not bonding are the lone pairs, okay? Now, you can also draw it like this, but the lone pairs are understood because we know the valence electrons. But for you guys, for now, go ahead and fill in your lone pairs, just so that you guys get used to knowing that they're there. All right, here goes an example. It says draw a molecule of chloroform, CH311, using solid wedge and dash lines to show its tetrahedral geometry. So I want you guys to go ahead and do that. Remember that tetrahedron that we drew before, where you have 2 in plane and 2 out of plane. All right, give you guys a little bit of time to do that. If you need more time, go ahead and pause it. I'm about to continue. Okay, so here you see chloroform. Now you could have drawn this with other ones in wedge or dash, so it will be also correct as long as you have two straight lines, a wedge, and a dash. In this case, it doesn't really matter. And later on, you'll see that sometimes it does matter. That's in a couple of chapters. But in this case, it doesn't matter which ones you put at the end. So this could have been a hydrogen, this could have been a chlorine, this could have been hydrogen or chlorine, whatever the case may be. As long as you have one hydrogen and three chlorines, your answer was correct. All right, so covalent bonds form when two atoms approach each other closely so that a singly occupied orbital on one of the atom overlaps a singly occupied orbital on the other atom. All right, so let's look at this hydrogen example, okay? So you have two hydrogens that are 1s orbitals. When they come close to each other, they're now occupying a singular orbula. The two singular orbitals are now occupying the same space, okay? When this happens, you are creating a sigma bond, okay? When 1s orbitals are combining together, you are creating a sigma bond. A little bit about bond length, okay? Because now you're creating a bond, so the distance between these atoms with this bond length can actually be, actually matters based on its stability, okay? So if it is too close, because the charges attract each other, they're going to repel. If they're too far apart, the bond is weak. So the distance between the two is going to be based on the stability, okay, for maximum stability. So there's actually computational chemistry software that can be used to be able to measure using different equations that have been developed over the years to be able to actually predict the bond lengths of atoms, okay? So in this case, for the hydrogens, it's 74 picometers. But depending on what atoms are actually being bonded, that bond length is going to be different. All right, so now we're going into chapters 1.12. Now, with chapter 1.12, we're simply talking about drawing structures. And I wanted to go ahead and move this to this point so you can start getting practice drawing structures. So, organic chemists, we want to be able to be efficient when drawing these structures. And so there are different methods for drawing structures. So let's look at these different methods. And then I'm going to show you guys the one that's the most common. So first, right here, you have your Coca-Cola structure here. And the Coca-Cola structure, you're showing every single bond that is being shared between the carbon and the hydrogen. And I want you guys to notice that the carbon always is going to be around 4. Each carbon has 4 bonds to it, okay? You can count those, 1, 2, 3, 4. Now, when you're looking at this is a condensed structure. So this is a little bit faster to draw because you're not drawing all these individual lines. And so if you look here, let me get I'm going to draw for you guys. All right, so if you look here, you have a carbon that's attached to 3 hydrogens. That is this CH3. Next, you have a carbon that is bonded to 2 hydrogens. That's this CH2. Then you have a carbon that is bonded to a hydrogen here, and then a CH3 up here. So this is this hydrogen here, the carbon hydrogen in the middle, and then this is that CH3 at the top. And then lastly, you have this CH3 here. That's the CH3 here. Now, you can also simplify it even more. We are looking at this here. This carbon here is actually bonded to CH3 here and CH3 here. So here you have your CH and it's bonded to two CH3s. And then on the other side, you have your, let's see, CH2, which is this CH2 here. And then your CH3, which is this CH3. So I'm going to erase everything here. And I want you guys to just take some time just to look at it and to process where everything is for yourself. If you need to, again, go ahead and pause it. So the most common way that you're going to see organic structures drawn out is using the skeletal structures, okay? So there's various rules for drawing out the skeletal structures. I'm going to list those rules, and then I'm going to show you an example. So carbon atoms aren't usually shown in skeletal structures. So you typically don't show carbon atoms, okay? Carbon atoms are assumed to be at each intersection of two lines. So anytime two lines intersect, we're making the assumption that there's a carbon atom in the middle of those two lines in that intersection. You're also assuming that there are carbon atoms at the ends of each line. Hydrogen atom bonds to carbons are not shown. Atoms other than carbon and hydrogen are shown. So with skeletal structures, you do not show your carbons or your hydrogens, but you do show all other hetero items. So that's your oxygens, your nitrogens, your halogens, anything else that's bonded, you are going to want to show those. All right, so let's look at some examples. And I'm going to pull my tablet up here so I can draw for you guys. All right, so let's first look at isoprene. Okay, so if you're looking at isoprene here, you're seeing that you have a carbon here. Let's see if I do it. So you have carbon here. You have a carbon here, carbon here, carbon here, carbon here. So if I'm doing the skeletal structure, I am going to draw my carbons exactly how I have them here. So I have a carbon at the end without drawing the actual carbons. So I have a carbon here. Matter of fact, I have a carbon here. I have a carbon up here, a carbon here, and a carbon here. Notice I didn't put any of my hydrogens on there. However, the hydrogens are understood. Now, what you do notice that you have to do is you do have to show the bonds. So if I have double bonds here and here, in my structure, I have to show my double bonds here and here. All right. So I'm going to erase this and I'm going to show you guys again. Counting them this time. So I have 1 carbon, 2 carbons, 3, 4. So I have a 4 carbon chain. 1, 2, 3, 4. And then I have an additional carbon. I'm going to call it A. That's not a part of the main carbon chain. Here, up here. Okay. So between carbon 1 and 2, as you see, I have a double bond. And between carbon 3 and 4, I also have a double bond. However, between 2 and 3, there's no double bond, or 2 and A, there's also no double bond. But your skeletal structure is going to look the same as your Coca-Cola structure, just without the hydrogens and the carbons written out. A habit that some students do is when they have the hydrogens, when they're converting it, they'll do this. That is incorrect, because once you draw lines, you're now making an assumption that these are carbons, not hydrogens. And so now if I have carbons there, that's completely different because then each of these carbons actually have to have hydrogens on them. So make sure you do not draw any lines. None of these hydrogen lines need to be drawn. So again, remember, none of these hydrogen lines need to be drawn. It's simply enough just to draw the carbons. And we can determine how many hydrogens will be on there. And I'm going to show you guys that in a second with the next example. So let's go down to the methyl cyclohexane. Okay, this is methyl cyclohexane. So now this time I'm going to show you guys looking at the skeletal structure and seeing how they got here. So if I look at the skeletal structure, I know that every single point, every single intersection, and every single end is a carbon. So I'm going to know that this is a carbon here, this is a carbon here, carbon, 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 and then at the end, I have a carbon. Okay. Now, once I have all my carbons, how do I know my hydrogens? Well, to know how many hydrogens you should put on there, you're going to count bonds. So this carbon right here has only one bond that is drawn. And remember, carbons are tetravalent. And so I need a total of 5. So because there's only one bond drawn, I know that there's actually a total of 3 additional hydrogens that are understood. Now this carbon here has 1, 2, 3 bonds attached to it. So to get 4, I know it's understood that I have 1 hydrogen attached to it. This carbon has how many bonds attached to it? 1, 2. Therefore, this is going to have a total of 2 more hydrogens up onto it. And if you go over here to this structure, you'll see the rest of them. This carbon is this carbon, which has 1, 2. And so I'm going to put an additional 2 more, which you see here. This right here also has 1, 2. So I have 2 more. This carbon drawn in the skeletal structure has 1 and 2 that are there and there. And so I get 2 more hydrogens that are understood. And last but not least, this also has 2. Therefore, it's going to have 2 there. All right, let's look at the next one. Now, this is what we call phenol. Okay, it's a benzene ring, which you guys will learn about, and then a OH group on there, the hydroxyl group on there, which makes this a phenol. And so if we're looking at this structure here, and we're counting bonds, let's identify where our carbons are. So while this is at the end, because it's attached to an atom already, there's no carbon here. This is simply an oxygen that's bonded to this carbon right here. Okay, so that is an oxygen that's bonded to this carbon. So this represents 2 electrons connecting this oxygen to this carbon. Now, if I continue on, this carbon is now attached to this carbon here, which is attached to this carbon, which is attached to this carbon, which is attached to this carbon, and this carbon until you get back to the top of the ring. Now, this carbon here is already bonded to, and I can even zoom in even more. Let's erase this. So this carbon here is already bonded to 1. There's another one here, 2. So you have to count both double bonds. 3, 4. So this carbon here already has 4 bonds. Therefore, there are no hydrogens attached to that carbon. And if you look here, this carbon does not have any hydrogens attached to it because it's already attached to 4 bonds. Now, when you go here, this carbon is attached to 1, 2, 3 bonds. So it is still missing 1. So I can actually put my hydrogen there. This carbon here, 1, 2, 3 bonds again. So there's going to be an additional hydrogen here. This is bonded to 3 as well. So there's going to be 1 hydrogen here. 1, 2, 3 again. Hydrogen here. 1, 2, 3. Hydrogen here. And so that's how we're able to know how to convert a skeletal structure into a cupola structure that you see here. Okay. Move it over just a little bit, just in case I'm blocking it. All right. So take some time, look at that, and see and count your bonds. Every carbon has every carbon has four electrons bonded, tetravalent. Every hydrogen has 1 bond. And then the oxygen actually has 2, 1 to the carbon, and then technically there's 1 between the oxygen and the hydrogen. So if you guys remember before, I was talking about how the different atoms can hold so many bonds while they're neutral with no charges on them. So the carbon has 4, the hydrogen has 1, and that oxygen over there has 2. And you know, for those, some people are visual. So let me show you what I'm talking about. So that hydrogen is bonded to the carbon, and then it's also bonded to that hydrogen here. That oxygen is bonded to the hydrogen there. And so that's what you're seeing there. And yes, there are lone pairs. Again, I know some of you guys are visual. So the lone pairs on this structure are not drawn out, but oxygen definitely has 2 sets of lone pairs on it as well that are understood. All right, so let's go to our example. How many hydrogens are bonded to each carbon in the following compound? Give the molecular formula for each substance. So we just have this one substance, which is estrone, which is a hormone. And I want you guys to, right now, go ahead and pause the video. And I want you guys to redraw this as a cupola structure, or at least identify, you don't have to, if you don't want to draw it completely out, take a picture of it, however you want to do it, screenshot it, and then go ahead and draw the hydrogens around it. Okay, go ahead and draw in all the hydrogens. That I want you to count your carbons, count your hydrogens, and don't forget the one that's already shown. And also, of course, your oxygens, and create the chemical formula. So I'm going to get started. I'm going to continue. So go ahead and pause it if you haven't finished. All right, so let's go around here. So this carbon, this carbon here would have how many? 3. Very good. There's a carbon here that's going to have 0. A carbon here would have 2. This carbon, 2. This carbon would have how many? 1. Very good. This carbon here, how many? 1. Very good. This one also would have 1. This carbon here, 2. This carbon, 2. Now this is a tricky one. How many would this have? Well, you see there's 1, 2, 3, 4 bonds, because that oxygen has 2 of them attached to it. So that's going to be 0 carbons there. 0 hydrogens there, excuse me. All right, so there's a carbon over here. How many would that have? 2. You have one here, 2. These two carbons both have 4 bonds also attached to them, so there's 0 hydrogens attached to those. This one would have 1. How many would this one have? 1 also. Here has 1. Now this carbon here has 0 because again, it's attached to 1, 2, 3, 4 bonds. Now we don't want to forget this hydrogen here, so we got to add 1 for that as well. So let's go ahead and count these out. How many carbons do you have? How many hydrogens do you have? How many oxygens do you have? And those are question marks, you guys. My question marks aren't coming in clear. So that would be your formula. So let's go to the next slide and see those. All right, so that's what we did. And if you count everything, you'll see that there's 18 carbons, there's 22 hydrogens, and 2 oxygens. The oxygens are really easy to see. Okay, so take some time to kind of look at that, counting your carbons and digesting it. And guess what? That is the end.